So if you recall, we introduced the concept of polar coordinates, just another way of keeping track of locations in two-dimensional space. Now we're going to introduce something that seems completely different and unrelated to this. So this is kind of Witcher season 1 style. Because we're going to go right from talking about polar coordinates to something that we don't see as being similar. Complex numbers, seemingly unrelated to polar coordinates. Let's talk about where complex numbers come from and what we need to know about complex numbers. If you recall, put your Wayback Machine to algebra and think back to radicals. Back when we was learning about radicals, we were told something like the square root of -9 is not a real number. Not that there isn't an answer. We're told that it's not a real number, which raises the question, what's a real number? A question that, for the most part, we don't ask, unless we think we'll be able to get under our teacher's skin and annoy them. And you're like, oh, Mr. So-and-so, why do you call these real numbers? What's a not real number? So we were told that the square root of 9 was not a real number. We didn't have to figure out anything more than that. It's not real. But this is unsatisfying for mathematicians. You can't just have like things. Is it really, does it need to be not real? Does it need to not exist like dividing by 0? Or can we work around it? So this is not a real bit. We can't just leave it alone. Square root of 9 is not a real number. We did not like this. So we invented something. It's like a what if we make something up? And we gave it like one of the worst names in math, but I can't think of what else we were going to call it. We spell imaginary. Hey Siri, how do you spell imaginary? It's an A-R-Y. No, I got it. I got it. Okay, I got it. Thank you. It's an A-R-Y. So let's invent some new kinds of numbers. And so we invented the imaginary unit. And we called it I. I is the square root of -1. That's bad grammar. I am the square root of -1. This is clearly not a real number because this is a number such that when we square it, we get -1. Clearly, this is no real number. Because it's a weird problem. When we square it, we end up with -1. So -9, or the square root of -9, we can calculate this by taking the square root of 9 and multiplying by the square root of -1. Like we do with when we're simplifying radically. The square root of 9 is 3. The square root of -1 is I. So the question is, it's not a real number, it's an imaginary number. Kind of raises the question, did we discover math or did we invent math? Is it discovery or is it an invention? Because if it's an invention, all numbers are imaginary numbers, because we just made that up. Like when someone says, that's not a word, that's a made up word. All words are made up. Someone had to make that shit up at some point. You know the thing that you rub on the board and it makes the writing go away? The eraser, that's a made up word. Anyway, similar questions with math. Do we invent math or do we discover it? These are weird kind of questions that mathematicians like to think about. So we learned that the square root of -9 was not a real number. No real number has the property such that when you square it, you get a negative number. So we like I was there, we invent these imaginary numbers. If I take 3i and square it, 3 squared is 9, I squared is I squared, but I squared is -1. Notice what we just did here. I had this new thing, this imaginary unit. And when I squared it, I did the same thing I do when I square anything else. I just like the exponent 2. Just like if it said the square of the product of 3 and x, I end up with 3 times x squared. So one of the things that we want to notice is we're going to treat I like a variable, but it's going to get simplified. I squared is replaced with -1. Treating it like we would x, some variable. We're treating I just like any other constant or variable, but we can simplify the powers of I. So I'm treating the I just like any other variable. If I had 3x squared, that would be 9x squared. The difference is when I have I squared, I need to simplify that because I squared is equal to -1. So if I have another example, like let's say I take this 3i and raise it to the 3rd power. Once again, just distribute the exponent over the product as one does. But now we've got I to the third power. We know that I squared is equal to -1. So I want to take out 2 of those i's and make a -1. And that will leave 1 I behind. So I'm going to look at this 27I cubed. There's the 27. There's an I squared times I to the first. That's what I squared represent. That's what I cubed means. It's an I squared times an I. The reason that we would want to do this is that I squared is -1. That door is reversed. Or it's working on its way up. I go over there and find the time traveling through the Enterprise. So we couldn't get the whale back. So we don't get the whale. Let's take a look at this 3i and raise it to the 4th power. Three to the 4th is just 81 like normal. But the I to the 4th, I'm going to break it up into 2i squared. And each I squared is a -1. So we can see we can always simplify a power of I. We'll either get ±1 or ±I. Odd ones will leave behind an I, the even ones will leave behind the plus or minus. Any questions? Imaginary numbers. Powers of I. We're going to treat it algebraically just like it was any other variable, just like if it was an x. But then we're going to take it one step further, and any power of I can be simplified to ±1 or ±I. We've only got those 4 choices. We have 1 power of I, we'll just have I. That'll be just I. We know that I squared is -1. I cubed, when we simplified that, we had -I. And then I to the 4th is +1. So here are 4 powers of I, ±1, ±I. These are the only 4 we need, because at this point, every time I have 4 powers of I, that's just 1. So if I have I to the 5th, we go further and have I to the 5th. That's just I to the 4th times I. So I to the fifth is just I. That means I to the sixth is going to be -1. I to the seventh, the -I, and I to the eighth. That's just 2 copies of I to the fourth. That's just 1 times 1. So that's just 1. And then it just keeps going around. If I have I to the ninth, that's just going to be an I to the eighth, which is 1, and 1 more factor of I. I to the 10th will be -1. I to the 11th will be -I. I to the 12th will be back to 1. All we need is those first 4, I to the first, second, third, and fourth. Then we can just look at the remainder of, when we divide the exponent by 4. So we only need these 4 results. Figure out which one it is. We divide the exponent by 4 and figure out what the remainder is. We're dividing by 4. We won't have a remainder of 4. We'll have a remainder of 0. If the remainder is 0, that means we have a multiple of 4. So that'll be the same as I to the 4th, 1. If the remainder upon division by 4 is 1, then we'll have I. If the remainder upon division by the exponent by 4 is 2, we'll have -1. And if the remainder upon dividing the exponent by 4 is 3, then we'll write -I. Every power of I can be written as plus or minus I or plus or minus 1. So for example, if we want to know what I to the 27th is, take the 27 and divide by 4. So we can subtract 4 from 27 6 times without going negative. 6 times 4 is 24. There'll be 3 left over. So the remainder is 3. So I to the 27th is equal to I to the 3rd. What we're doing is we're taking 4 groups of 4 factors of I, because 4 factors of I is equal to -1. Sorry, 4 factors of I is equal to 1. Question? How's everybody okay? So we're going to treat it just like a variable, but we're going to simplify powers of I. These are all imaginary numbers. And I set the title of this section as complex numbers. So what's a complex number? A complex number is a combination of a real number and an imaginary number. So a complex number has the form a plus bi, where a is the real part and b is the imaginary part. Note that the imaginary part of the real number is the imaginary part of a complex number is a real number. It's multiplied by I, and that makes that term imaginary. So we have an imaginary term. The imaginary part is a real number. So for example, 2 minus 3i is a complex number with real part 2 and imaginary part -3. So we've got this whole new number system where the numbers look like a plus bi. If a is 0, then the number is pure imaginary. If b is 0, then the complex number is a real number. Real numbers are a subset of complex numbers. If there's no real part, then the complex number is pure imaginary. All imaginary parts. If b is equal to 0, then the complex number is real. Real numbers are a subset of complex numbers. This is called a Wizard of Oz scenario. You've been dealing with complex numbers the whole time. They've just been real numbers. We just had imaginary part 0 for this whole time. Although it's a lot less useful than the Wizard of Oz scenario. You already seen the Wizard of Oz? She had the power to go home the whole time. All she had to do was click her heels together and say there's no place like home or something. Oh, dude, why didn't you tell me that at the beginning of the movie? Then we wouldn't have found out that the real adventure was the friends that we made along the way. What are we talking about? Oh, yeah. So we've got this new number system. That means we need to know how to perform operations on our new number system. So that raises the question, how do we work with these new numbers? What are we going to do? How do we add them, subtract them, multiply them, divide them, raise them to exponents? Here's the good news. It's exactly what you would think they are. They look like little binomials. Just do binomial shit. It's that simple. You already know how to work with complex numbers. You've been training for this moment your whole algebra lives. They're just polynomials, and you can simplify the powers of I. It's just one more step on top of polynomial stuff. So for example, let's say we have one complex number is 2 minus 3i. And another complex number is 1 plus 4i. Here are a couple of complex numbers. It has all these different streets that it comes to. It's like one of those car alarms that have all the different car alarms. They just combine all the car alarms into one car alarm. So play each one for the person who is in charge of coming up with the sound of the car alarm. Like, oh man, these are all great options. Just string them all together. Play each one for like 5 seconds. Does anybody even react to car alarms anymore? Like if a car alarm is going off, we're like, oh no, there's a car in trouble. Other than, do we react like in that way? Like in the way the alarm is supposed, like if the fire alarm went off, we'd be like, oh, there's a fire alarm, a fire somewhere. We should go, right? And so we leave. But if you do the drills too often, people are like, another fire drill, so we just leave. It's kind of programming. And I think the goal is to make the sound in the room so annoying, people just want to leave anyway, so they don't sit through a fire. I don't know who would do that. But anyway, when we hear car alarm, do we worry that there's a car in trouble? Or do we just think, man, I hope that person shuts off their car alarm? I mean, there could be a car being stolen at this moment. You're like sitting in your house and all of a sudden outside on the street, that sound happens. Whoop, 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 bleed off, bleed off. And we're like, oh my gosh, the car is in trouble. We don't rush to the window and like look out. What's going on out there? There's a car in trouble. Maybe we should go. We just like, oh man, that's annoying. Imagine if we did that with people. Like we're sitting in here and then we hear like this thump, 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 thump. And then we hear a sound coming from out the door. It's like, oh my God, I fell down the stairs and broke my leg. Help. I'm like, oh man, I wish that person would just shut up. We'd probably go out there and check on him, you know? Of course, this is America, so we probably do. Close the door. Come on. Cool. We'll go out the back. We don't want to get involved. You know what I mean? This is how I know that humans are a garbage species. You ever go through the internet and find some uplifting story And people say, oh, this is restored by faith in humanity. Because one person did one nice thing. Here's why that is a terrifying thing. That kind of thing happens so infrequently that we notice when it happens. We are so garbage of a species that one person does something moderately nice for another, like a selfless act, and we're like, oh, wow, did you see that? Meanwhile, if we weren't a garbage species, that would just be normal and we wouldn't point it out. You know what I mean? So, QED, humanity is garbage. Because we're capable of doing good things, and we all recognize it as good, but it happens so infrequently that we feel compelled to call it out when we see it. Anyway. What are we talking about? Oh, yes. That was all delay tactics to give you a chance to think, what the heck are we going to do with these weirdo complex numbers? We're going to do the same thing that we would just guess. 2 plus 1 is 3. We combine like terms. -3 plus 4 is +1. We wanted to subtract them. Two minus 1 is 1. -3 minus 4 is -7. Just like we would anyway. This is what we would have guessed is going to happen. This is my favorite thing to happen in a math class. When what we guess should happen is what happens, that's best. It's like, aha, we knew it. Humans always enjoy that one. We complain when there are spoilers, but we also complain when we saw it coming, even though it's very satisfying when we saw it coming. It's even better with this subtraction. If I reverse the order of subtraction, that should change the sign of my result. 2 minus 3 is -1, but 3 minus 2 is +1. So if I change the order of my subtraction, I just get the opposite of what I had before. 1 minus 2 is -1. -4, oh, it's +4. 4 minus a -3 is +7. These things really are just behaving like numbers. This is all as expected. If I want to multiply these numbers, this is also exactly like we would expect it to be. I have a binomial times another binomial. I just run multiplication. Make sure each term of one polynomial is multiplied by every term of the other polynomial. So 2 times 1 is 2, plus 8i, minus 3i, minus 12i squared. That's if we just multiply it like polynomial. But we have to remember that we have one extra step because we're dealing with complex numbers. And I squared is -1. Same multiplication that we would always use. Same multiplication that we used when we first learned how to multiply numbers. Even if I set it up vertically. This is just another way to keep track of what's going on in our multiplication. 4i times -3i is -12i squared. 4i times 2 is +8i. 1 times -3 is -3i. 1 times 2 is 2. Even if you like to multiply in boxes. I don't know anybody that likes to multiply like this way, except for me. But it's just a way, we just need a way to keep track of each term of one polynomial getting multiplied by every term of the other polynomial. 1 times 2 is 2, 1 times minus 3 is minus 3i, 4 times 2, 4i times 2 is 8i, 4i times negative 3i is negative 12i squared. Box method is cool because you can do it in reverse to help you factor polynomials. That reinforces the idea that factoring is just unmultiplication, undoing multiplication. We already know how to perform operations on complex numbers because we learned how to perform operations on polynomials. And this is just polynomials with extra stuff at the end. So 2 minus 3i squared, you just treat this like a binomial, a square of a binomial, and multiply. Extra step, I squared is negative 1. So I have 4 minus 9 is negative 5 minus 12i. Question? How's everybody okay? I'm just totally fascinated by complex numbers. Wow. Square root of negative 1. Whoa. Sometimes math, even the really cool math like this, as cool as this is, I feel like I'm like the only person that thinks it's cool. You know what I mean? And there's like this disconnect between the writer and the audience, just like it happens, like the last season of Game of Thrones. I'm sure they thought they were doing something really cool. And they go, wow, this will be really cool. And they're like, oh, here it is. And everybody's like, oh, nah, we don't like that. Like, oh, damn. Big disconnect. Same kind of thing. Complex numbers, isn't it rad? And everybody's like, oh, no, this is bad. The difference is people with money don't have to give them money to do projects anymore. And y'all are stuck with me. What if you could vote me out of the classroom? Like, nope, this teacher is not doing it. Let's interview another teacher. We can all just get together. And I'd like walk in here one day and there'd be another person setting stuff up here in my home. Who are you? And then one of your representatives go, sorry, Lee, you got voted off the island. Like, where did you get that torch from? And you're like, oh, no, you gotta go. Like, well, hang on, but you're like, get out. I go, all right. I'm gonna take over some other class. Question? I wouldn't actually take over another class. I would send people to people's class. I learned that when I was teaching high school. Now, if you can imagine me teaching high school, this is an extraordinary, and you think this is an extraordinarily bad idea, you are absolutely 100% correct. This is an extraordinarily bad idea, but I did it anyway. So at one point, we had, at my high school, we had these whiteboards like this. And rather than carry around our own pens, we just kind of like leave pens on the tray. Right? I don't know why we thought this would work, but it didn't for the most part. Because lots of teachers say, this pen doesn't work anymore. Put the cap back on it and put it back in the tray. So next teacher will walk in and say, oh, I'm glad there's a pen here. They're like, oh, it doesn't work. And they go, who had this class before? So anyway, we were running out of pen all the time. So I'm sitting there and my students are taking the quiz. It's nice and quiet. And the classroom is set up roughly like this. There's an entrance on either side of the board. And the audience is out there. So I'm sitting there watching the quiz proceeding. And in walks some other student that is not in this class. They walk in, they don't say anything. They're walking in, right up next to the board, grab a couple of pens, and walk out the other side. Never said a word. I was stunned. I was like, oh, waiting for you to explain why you're taking pens, and now you're leaving. You never asked, just walked in and fucking took them. And I was just like standing there, what was that? I'm like shocked. And one of my students is like, oh, you gonna take that? I go, well, no. Anybody know that guy? And they're like, well, yeah. And you didn't say anything? I go, well, we had, I was just as shocked as you. But he's in Mrs. So-and-so's class upstairs. Oh, right above us? I go, yeah. All right, who's done with the quiz? I need a recovery party. Send a student to steal my pens. I'll send a team of students to steal them back. So I got a bunch of volunteers. It was not difficult because shenanigans were afoot and they were high school boys because it was an all boys school. So they were all in. Of course, some of the volunteers had not finished their quiz. They just wanted to go do something else. So, and I should have known this. As McFadden gets up, Michael, this will be fine. I knew it was not going to be fine. So anyway, I'm like, all right, this is what I want you guys to do. One at a time. Go in one door, grab one pen, walk out the other door. This will be fun. I won't be able to see it, but it'll be fun, right? So one at a time. One person will go in, grab a pen, walk out the other side. As soon as they clear the other door, next person come in, grab one pen. And it'll be funny because it'll be a procession of what I planned to be like 5 people coming in and getting my pens back. Instead of sending a party of 5, I didn't really do a head count. I ended up sending like a dozen guys upstairs. And it went fine. Based on what I heard, it went fine for about 30 seconds. That's when I remembered no plan survives contact with the enemy. First, I think the first 2 went through okay. But as soon as the third one went in, I heard this all, hey, blah, 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 blah. And then I heard thump, 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 thump. I'm like, oh, this has gone horribly bad. And it was extra good because I was on the ground floor, right across the lobby from where the administration was. And I just sent my team to the lobby upstairs, grabbed the pen, and they were on their way back. I go, well, I'll just deal with this fallout later. The administration already doesn't like me, so it's fine. It's fine. My team comes back, and the first one through the door comes back with like 5 pens. I go, guys, I say grab 1 pen each and walk out. Grab 5 pens. The next one came back with both the erasers. The next one came back with a garbage can. I'm like, oh, guys, does that look like a pen? And they were like celebrating because they have the spoils of war. And I go, yeah. And then, of course, my class is cheering them on, which is only going to make things worse. And I go, yes, revenge. One of them had a box of fucking papers that Miss So-and-so was going to bring home the grade. I go, guys, you can't just walk in and take stuff. And I go, you told us to do it. Not this. We put some liberty. All right, everybody sit down, be quiet, be cool, act like nothing happened. All right, everybody be cool. I looked out the window, and here comes the dean of students. after hearing all the commotion. I'm like, everybody sit down, be cool, be cool. And so I'm sitting there, we're taking the quiz. John pokes his head in. Is everything okay? I thought I heard something. No, everything's fine. We're all good. We like looked at all our spoils sitting off in the corner. And I don't know where that came from. So anyway. It only escalated from there. And it was really bad because they had the high ground. But I had juniors and seniors. And she only had sophomore. So we had a, you know what I mean? Anyway, what were we talking about? Oh, yes. I shouldn't be allowed to teach high school. All right. So what we need to do next is figure out what the connection is between these complex numbers and polar coordinates. Well, we're gonna save that for another day. So next time, complex numbers. Why did we talk about polar coordinates before getting into this complex number business? How are these two story arcs going to intersect? That's it for today. That's it for this week. I'll see y'all on Tuesday. Everybody have a good weekend. And thanks for playing.